Hello, I'm Lauri Juvela, presenting our paper Audio Codec Augmentation for Robust Collaborative Watermarking of Speech Synthesis for ICASSP 2025. We've seen that modern speech synthesis is quite good in quality and can be used for voice cloning. This presents some cases for misuse. The research in speech deepfake detection in the anti-spoofing context has progressed a lot in the recent years, but these becoming classic detection approaches are all based on a kind of a passive detection setting, whereas we think we should also investigate some active measures of making the generated speech easier to detect. And this is also tied with a new EU AI Act regulation on that providers of AI systems generating synthetic audio or other content shall ensure that the AI systems outputs are marked in a readable format and detectable as artificially generated. This is a recent example of a Finnish AI-generated meme of a late Finnish president doing a talk show. It's quite funny and the quality is convincing. It's obvious that it's fake from the context, but this may not always be the case. And the screenshot is from the Finnish national newspaper Helsingin Sanomat. They added a label explicitly saying this is made with AI, but these kind of labels can be easy to remove, and in this setting, the audio isn't marked at all. Yeah, in this paper, we're first looking at a traditional matched deepfake detector setting, where we have a generative model here on the left. It's a hi-fi GAN. It's taking a smell spectrogram, generating a waveform that we want to detect as being generated. It's being passed through an audio codec, which hinders the detection somewhat, and then we'll have a detector model that is kind of detached from the generator. There's no communication. The codecs detaching things or like making sure that there's no gradient flow. And in this setting, there's no communication there, so the detector is dubbed the observer. Yeah. Then in this other setting, we are changing to an active mode. It's otherwise the setting's identical. We have a generative model here on the left, a generator that's working against the discriminator as its training objective. It's generating a waveform. It needs to be passed through an audio codec, and we have a detector model here that is otherwise configured the same. It's also trying to detect whether it's like real audio or generated audio coming from hi-fi GAN. But now we are setting the generator to help or collaborate with the detector model, and this is why we call the detector now a collaborator. And another complication in this is that we also need to be able to pass gradients from the collaborator through the transmission channel back to the generator. And in general, the codecs are not differentiable. If we use a kind of a black box MP3 or speech codec, we're using the Opus codec, an MP3 in the experiments, or some neural audio codecs, which are differentiable by design, but classic codecs are not. So we need some way of approximating gradients through this, and turns out that we can use the kind of copy gradient estimator to pass information back through the generator through a codec as a transmission channel. So how do you do that? How do you make a codec differentiable or approximate gradients through it? Turns out that a very simple recipe is effective for this. It's just really copying gradients with a straight-through-estimator. So basically on a forward pass, you take your kind of original signal, generated signal, and then your coded signal, and a version of the signal that has gradients detached. So these two are identical. They cancel out on the forward pass, and you get the kind of signal coming through your codec on the forward pass. On the backward pass, just kind of looking at the terms individually, you see that, yeah, gradient for the codec, it's cut because the codec is not differentiable. Then you'll have the detached gradients also 0. So the only gradient you'll get through is this the original impulse gradient. So this kind of neat and standard way of implementing the straight-through estimator. Yeah, now for some kind of specifics on the experimental setup, we're working with a hi-fi gain vocoder and all the kind of discriminator configurations also kept when training these models. The detector we're using, Assist, that's kind of a state-of-the-art SV spoof anti-spoofing detector model. For the codecs we're using MP3 and Opus in different configurations, and Vorbis for testing stage. We're doing this at different bit rates or quality configurations, so 16, 32, 64, and 128. And additionally, we're using a neural audio codec, a pre-trained DAC audio neural audio codec at 8 kilobits per second. And all of these models we start from pre-trained and fine-tune these when possible, with some modifications needed for the assist batch normalization and so forth. Yeah, let's start looking at the big results table of equal error rates, or EER. First thing about reading this is like, don't necessarily look at the numbers, look at the shades. This is a color coded, so like a light color is good performance. Darker shades are bad. And then we'll have evaluation conditions as the rows. For example, let's first look at the result that compression is challenging, or let's say MP3 at a high bitrate of 128 is like, without codec augmentation or augmenting with different codecs at different bit rates, we'll still get pretty good performance through like a high rate codec. But once you start lowering the bit rate or compressing more, the performance degrades gradually. Then another contrast to look at is the differences between observer mode training and collaborative training. In this case, the highlighted columns are using no augmentation for codecs, and at high bitrate both systems perform quite well on the scene conditions, but we'll start seeing differences for like unseen codecs or the DAC neural audio codec. It's consistently using collaborative training leads to better detection performance, and but we still have fairly poor generalization for the kind of more compressed settings. Another thing that we can see from this is that augmentation does improve generalization. This column we're listing as all includes MP3 and Opus at all of the listed bit rates without Vorbis or DAC. And collaborative training seems to generalize quite well for testing with DAC if we're augmenting with all of the classic audio codecs. And if we look at the setting where we're augmenting only using the DAC neural audio codec, we see I think quite a surprising positive surprise result that both in observer and collaborative settings we see quite good generalization, especially with a collaborator on the kind of unrelated DSP audio codecs, and also not so great for Vorbis, but for Opus and MP3, even without seeing these codecs, augmenting with DAC gives pretty good generalization for detecting through MP3 and Opus. And this is also nice because the DAC is kind of, our neural audio codecs are naturally built in a differentiable way, and we don't need to be approximating gradients and so forth. To rate the effectiveness of augmentation, it's useful to make comparisons in matched conditions against the no augmentation baseline. So in this case, look at observer mode training without augmentation, and let's say in this case all of the augmentations. And well, on average, you get better performance at low rates or high compression. You get somewhat improved results. Whereas for high bit rates, the performance actually drops a little bit. Doing the same comparison in observer mode for no augmentation versus using the DAC. Yeah, this is maybe even a kind of a brighter picture. That it's like for low compression, the performance is similar, slightly worse, but you get much improved performance for higher compression rates and even for the Vorbis unseen codec. Doing similar comparisons against no augmentation versus different augmentation scenes. Like, let's use all of the DSP augmentations, but now in collaborator mode. The picture, well, we see that augmentation works, but the numbers are pretty much better for the collaborative training across the board. Similarly, for collaborative training with the DAC augmentation versus no augmentation, the results are quite good for almost all of the settings. Still not so great for low quality Vorbis, but I think I was surprised to see this for the Opus and MP3. See pretty good generalization. Then the other thing to look at, how does this affect the subjective perceived quality of the system? In this setting, the observer training does not affect the quality because there's no information flow from the detector. So for all of the observer settings, we can look at basically the vocoded speech, whether like pre-trained hi-fi GAN sits here, then all of the observer mode systems are basically at the fine-tuned hi-fi GAN level, and then we can look at the different collaborative systems at different bit rates. But for high bitrate systems or through the DAC or no augmentation at all, we are kind of at the very similar MOS quality level compared to the pre-trained and fine-tuned systems, and we start seeing a quality drop when we're using lower bit rates for the codecs or all of the codecs. Another thing that we see is that like using all of the codecs versus just the lowest quality is very similar perceptually, because the system needs to kind of prepare for the worst case when it's seeing like a pool of all of the conditions. It's kind of matching the worst case. So the conclusions: augmentation with audio codecs improves the detection performance generally. Usually collaborative training improves detection performance over the observer passive mode, and augmentation at high audio codec bitrates does not cause a significant quality drop in subjective tests, and we see that the DAC neural audio codec augmentation generalizes surprisingly well to other codecs. Thanks for listening.